All right, so this problem says a commuter backs her car out of her garage with an acceleration of 1.4 meters per second square. How long does it take her to reach a speed of 2 meters per second? All right, so part A. And you'll see that in a lot of our problems, we'll be using these four equations, kinematic equation, these equations. Okay. So here's the commuter. All right, so she starts off from rest and she accelerates in this direction, and there's a final velocity. Okay, so the acceleration is constant. Okay, and so we can use our kinematic equations. V equal to V naught plus AT. And they're asking you how long does it take her to reach that speed. So they're asking you for the time. What was her initial speed? 0. Okay, so T is V minus V naught divided by A. So 2 meters per second minus 0 divided by 1.4 meters per second squared. Okay, the 1 meters per second cancels. You have a second left, and then that goes on top. So this is equal to so 1.43 seconds. Okay. So it takes her 1.43 seconds to reach that speed. If she then brakes to a stop in 0.8 seconds, okay, so it took her that amount of time to accelerate to that, and she brakes in 0.8 seconds. Okay. Now that's a common feature. Okay, that's a safety feature. Your deceleration rate, when you brake, you're stopping, your acceleration is much higher than that. Okay. You want a higher acceleration, what do you have to do? You have to shell out more money. Okay. That thing costs money. This thing is a safety feature. That's for the safety of everybody around you. They'll provide for free. Okay. All right, so let's find out the deceleration. Now, we're going to use the same equation. Okay, what is the final velocity this time? Okay, so here you're going at 2 meters per second and you ended up there. Your final, now this is the journey. Okay, so this is 2 meters per second. What is your final velocity this time? 0. Yep. So you're coming to rest and you're finding your acceleration this time, V minus V naught divided by T, 0 minus 2 meters per second divided by 0.8 second. And so this is 2.5 meters per second squared. Okay, so a couple of things you want to notice. So when you're braking, the acceleration is a lot higher. Okay, so it's 66% higher. What does the negative sign tell you? It's in the opposite direction of the velocity. Okay, so when you're braking, the acceleration has to be in the opposite direction, so that's deceleration. All right, here's another useful exercise to do. Okay, so make sure you understand this. What I'm going to do is I'm going to write 0.25 meters. That's your acceleration. I'm going to do this. Multiplied by g, divide by 9.8 meters per second. Yeah. I just want to show you this trick. Okay, so let's add a page. Okay, why am I doing this? Well, what is this? Is this legal? Can I do this? Well, why can I do this? Very good. No, so this is 1. All I'm doing is multiplying this by 1. Okay, why am I doing this? Well, this cancels. So your acceleration is minus 2.5 All right, why did we do this? What is your weight? mg. Okay. What is half your weight? Okay. So you see, the decelerating force is a quarter of the weight of the car. Yep. So that's what that is. Okay, so what I want you to get in the habit of, so we're going to attempt to do this over the entire course of the semester. You want to start giving meaning to the answers. Okay? An answer is not just a number anymore. Okay? A particle has a constant acceleration of 6 meters per second square. If its initial velocity is 2 meters per second, at what time is the displacement 5 meters? So they're asking you for the displacement and what is its velocity at that time. Okay, so here is the formula for the displacement. Okay, so they give you the initial velocity is 2 meters per second, and soon I won't write units. You will I'm not going to write units here. So the displacement 5 meters. Okay. Okay, so you just have to solve this quadratic equation. So that's 12 times, 12 times 5 is 60, 64, square root of 64 is 8. Divided by 6. So that's 6 divided by 6 is 1 second, or minus 10 over 6, that is minus 1.67 seconds. All right, so this will, the initial velocity was 2 meters per second. After 1 second, it'll, with that acceleration, okay, it'll reach 5 meters. It'll be 5 meters away. Okay, so that's what, now I'm going to show you something. I mean, it's a little subtle, but what is this solution? So your mathematics gave you two solutions. This solution was if you go at 2 meters per second, there's the acceleration, you end up 5 meters away. Well, what is this guy? I'm sorry? Right, so let's try and give meaning to that solution. Why? An hour ago you were minus 1 hour old. T minus 1 hour old.
So that's where it was 1.67 seconds.
All right, so let's figure out what it is. Okay, it's slightly subtle. Okay, so if t is negative, see this term, if t was negative, this term is still positive. If this were negative and this is negative, that term becomes positive. That's the same equation as that. All right, so what this is saying is, if you start off with minus 2 meters per second, 1.67 seconds ago, and you had this acceleration, again, don't worry about it if you don't understand it, you go like that, and you would be there at time t equal to 0 seconds at 5 meters. So in 1.67 seconds, that's where you'll be, all right? For our purposes, all you have to do is this is your solution. Okay? But the reason I pointed that out is because all solutions will have, most of the time, all solutions will have meaning. Okay? Sometimes it's a little subtle, so you have to be careful.
So we're only writing positive one as an answer, you said?
Yeah. So freight trains can produce only a relatively small acceleration. What is the final velocity of a freight train that accelerates at 0.05 meters per second square for 8 minutes, starting with an initial velocity of 4 meters per second? Okay, so here's the final velocity. The initial velocity was 4 meters per second. The acceleration is 0.05 meters per second square. Okay, I'll write down units. And what is the time at which you're finding the acceleration? I mean, what is the time at which you're finding the velocity? 8 minutes. You have to convert that to second. 480 seconds. Okay? So it's going at about 28 meters per second. And here's a good thing to remember, sort of 10 meters per second is roughly 25 miles an hour. So this is about 75 miles an hour. Okay. Now, again, if the train can slow down at a rate of 0.55 meters per second square, you see, again, this is a safety feature. The deceleration, the braking acceleration is 10 times greater than that. Okay. This is a excitement stuff. This is a safety stuff. Okay. Okay, so now you want to come to stop, and your deceleration is so your initial velocity was in this direction, which was taken to be positive, and the acceleration is in that direction. So you're stopping in about 1 minute, less than 1 minute, okay? So how far will it travel in each case? Okay. So for the first case, the time of travel was 480 seconds plus 1/2 0.05. So about 8 kilometers. So it's speeding up from about 10 miles an hour to 75 miles an hour. And this distance, 8 kilometers, is from here to Granada Boulevard. Okay, so that's how long it takes for this train to speed up. And then slowing down, how long does it take to okay, C2. Now you're going at 28 meters per second, and you're stopping, and your deceleration is negative 0.55 meters per second square. X minus x naught equal to v naught t plus 1/2 at squared. 28, oops. And what is the time of stopping? 50.9 seconds. So your stopping distance is that. All right. So let's do the following. Okay, so here's another formula that you've seen. So here's the final velocity, here's the initial velocity squared, 2 times the acceleration times the distance over which this acceleration happened. So you see if the acceleration, so in this problem, the stopping acceleration was 10 times greater than that, 11 times greater than that. So if your acceleration is 11 times greater, your stopping distance would be 11 times smaller. Okay. You might have experienced this if you, well, nowadays all cars have anti-locking braking systems, but when you have anti-locking braking systems, you are using static friction to stop your car. That gives you a greater deceleration. The stopping distance is smaller. Okay, and so the insurance people will give you a better rate. All right, so this problem says a woodpecker's brain is specially protected from large accelerations by tendon-like attachments inside the skull while pecking on a tree. While pecking on a tree, the woodpecker's head comes to a stop from an initial velocity of 0.6 meters per second in a distance of only 2 millimeters. Find the acceleration in meters per second in multiples of g. Okay, so here's a woodpecker, here's a beak, and the woodpecker is going at 0.6 meters per second. And it stops over a distance of 2 millimeters. 2 millimeters is that much. Okay, so we'll find the deceleration of the head. Okay, so we can use v square equal to v naught square plus 2a x minus x naught. So the acceleration would be v square minus v naught square divided by 2x minus x naught. 0 minus 0.6 square divided by 2 times 2 millimeters is a millimeter is a thousandth of a meter. Okay. Okay, so the force that is stopping the head, the force exerted by the tree that's stopping the head is 9 times the weight of the head. Okay. Now, if you hit the brain with 9 times the weight of the brain, you're certainly going to get a concussion. Okay? And if you're doing this 1,000,000 times a day, you're not going to last too long. Okay, so oops. So here's the here's the tree stopping the head. Here's the brain. Generally, your brain is suspended in a fluid. Okay, so let's say the head is going at 2 meters a second. What is the speed of the brain? 2 meters a second. The head comes to a rest. What happens to the brain? It's still going at 2 meters per second. Okay, the liquid will slow it down. Okay, and then it'll hit the skull, and you get a headache. Every bug is going to cost you a headache. All right, what you need is an airbag. These are elastic rubber bands. For real. So when the brain is trying to go down, these guys stretch and pull your brain back. And they soften the blow. Okay? All right.
It's blank.
Okay, so calculate the stopping time. Okay, so we'll calculate the stopping time. Okay. You see, smaller the acceleration, greater the stopping time. So all safety devices, what they're about is giving you a smaller acceleration. Okay? They're all, what does an airbag do? It stops you over a greater time, giving you a smaller acceleration. Smaller accelerations cause less damage. Okay? So for this case, the stopping time for the skull was 0 minus 0.6 meters per second divided by 90 meters per second squared. Okay, so the stopping time for the skull was 6.7 milliseconds. Okay. Now what we'll do is, so the tendons cradling the brain, like I said, the tendons cradling the brains. Huh? Okay, so these are sort of the airbags for the woodpecker. So the tendons cradling the brain make its stopping distance 4.5 millimeters. Okay, so here's a simple thing. All right, so now you increase the stopping distance to more than twice the original distance, from 2 millimeters to 4.5 millimeters. Okay, and that's what your airbag is doing. What is your airbag doing? If you didn't have an airbag, what is stopping you? I'm sorry? Your steering wheel, okay, which will, there's not a whole lot of give there, and it stops you fairly fast. And the airbag increases your stopping distance, decreasing your acceleration. So for the brain, the stopping distance doubled, so your acceleration decreased by a half. So instead of 9 Gs, you'll be facing 4 to 5 Gs. Okay. All right. So the tendons cradling the brain stretch, making its stopping distance 4.5 millimeters. Okay, so C. Okay, so the skull is experiencing 9 Gs while the brain is experiencing only 4.44 Gs. Okay. And since you still see plenty of woodpeckers around, I guess that's safe enough. They're not flying around with concussions. Yep, yep.
Why did you divide by -90 in part B?
I'm sorry?
Why did you make it a -90 in part B when you were dividing?
Oh, well, the velocity was in this direction, and the acceleration was in the opposite direction. All right, maybe I might do 2 more problems. So let's do this one. A hot air balloon rises from ground level at a constant velocity of 3 meters per second. 1 minute after liftoff, a sandbag is dropped. Okay, so it Okay, so a hot air balloon is rising at a constant velocity of 3 meters per second. So what must be true when, if it's rising at constant velocity, there's the weight of the hot air balloon? Why isn't this decelerating the balloon?
There's a force pushing against the weight.
And how big is this thrust force?
Slightly larger than gravity.
It's exactly the same as gravity. If it was larger, then it would accelerate upward.
Sure.
Right. All right, so that balances the force of gravity, and it is traveled for 1 minute. 1 minute is 60 seconds, 60 times that is that, so that's 180 meters. So after 1 minute, it's at a height of 180 meters. Okay? 1 minute after liftoff, a sandbag is dropped accidentally from the balloon. Okay, so you stick your hands out and drop a sandbag. What happens to the sandbag? All right, so let's do the following. We're going to drive on 95 at 80 miles an hour. You're going to stick your hand out and drop an orange, what is the orange going to do?
Falls down.
It's
Still have its momentum.
it's going at 80 miles an hour. So just like that, when you drop the sandbag, it's going at 3 meters per second. Up. So it'll go up, its velocity will get 0 and then come down. Okay. All right, so it's dropped accidentally from the balloon. Calculate the time it takes for the sandbag to reach the ground. Okay, so we'll calculate this time. All right, so again, we'll set up our axes such that okay, so we are just calling this y-axis. What is the final y position? Very good, 0. The initial y position, 180 meters. The initial velocity is 3 meters per second. And what is the acceleration? There's the axis. The acceleration is negative 9.8 meters per second square. All right. So again, all right, so what is it that we're finding? If this is t equal to 0 seconds, after 6.37 seconds, it will be on the ground. Well, what is this fella doing? So what is this fella? Let's figure that out. Now, if if you threw the sandbag from the ground at the appropriate velocity, and it was decelerating, and when it got to that point, it was going at 3 meters per second, that would be 5.77 seconds ago. Okay. So it'll be on the ground again. That's the other solution. Okay, so that's what that solution is. All right.
You've been saying the little g, you mean like gravity, that's why you're raising.
That's the magnitude of the acceleration g. Yep. All right, guys, this is enough for today.